CLI and a cross-platform IDE for C and C++. Download now.
Hello, everybody. Good to see you. I'm talking about something that's pretty old, which is the Chrono library, but it's amazingly, well, it's interesting to use it. And I want to help you to find out how and where the caveats are and how you have to deal with it. And at the end, the goal is we want to answer the question how old I am in seconds, which is surprisingly tricky to do. Well, it's not a lot of lines of code, but to understand what's going on. So when we see the different versions of C++, then it turns out that the Chrono library came in 2 steps into the C++ library. So one was with C++11, the basics with durations and time points, and then with C++20 formatting stuff, formatted output support, calendars, time zones, and other things. So, and to understand how to deal with that library and about its awesome design by Howard Hinand is let's first understand how we deal in this library with the question or with the statement. Let's meet tomorrow 10 minutes earlier. So think about how this is handled in your brain. So human beings say, oh, that's plus 24 hours minus 10 minutes. That's the way we can understand that. That's the way we can deal with that. Now, the usual approach that standard libraries and programming languages of any kind have is, let's, in a computer, let's use just some very fine-grained data type that can deal with all the possible values. And so if you do that in seconds, for example, it would mean that we internally have to use 85,800 seconds for this duration. And seconds was a time when sleep was standardized by C, so that we could sleep a program and pass a program in seconds. That was 30 years ago or so. So times have changed. But even with that second unit, we need more than 2 bytes. 2 bytes are not enough for this duration then. So if we get more and more fine-grained, we might switch to milliseconds. Then we need more than 3 bytes. We might switch to microseconds. We need more than 4 bytes. So that's a significant change, because then maybe on a 32-bit platform, we no longer can use the native data type. And then when we switch to nanoseconds, which a lot of hardware currently supports as granularity, we have to use more than 5 bytes. So at least 6 bytes for that. And that's only 24 hours. So let's talk about 100 years, then it gets worse. The approach of the Chrono library is different. The approach of the Chrono library is, let's use the best unit to represent the result, to deal with the possible values. And in this particular example, that would mean let's use 24 hours. That needs 1 byte for the value. Subtract 10 minutes. That also needs 1 byte for the value, just a different unit. And then for the result, we need something in common because we combine hours with minutes. So here we need 2 bytes. That's it. And that, of course, saves a lot of memory. And that's one of the major goals of this library, having good performance, which means good speed and not too much footprint. So how is this programmed in the Chrono library? Well, if you declare something like A being 24 hours, you need just a type that can hold the 24, which could be a very small int. The standard type here is a little bit bigger, but that would be enough. And the internal type is I am a duration. I'm using an integral value, and I have a unit, and that unit is a fraction in seconds. So in our situation, it's hours, so it's 3,600 seconds. That is the unit of this. The unit is a type. The type is not there at the end when the program runs. So when running, just a SHA would be enough to hold this value. Minutes, same way, it's just a different unit. So we have 60 seconds as units, so a different ratio here. And now, if you compute the sum of both, then compile time magic happens because we need the resulting type, which means we need the resulting unit. And the resulting unit has to be perfect to express all possible results, but on the other hand, don't waste too much memory. And the compiler will compute here because one type fits in the other, so that we can use minutes here for the result and generate corresponding code that we have to multiply the value of A with 60 and then add the value of B, and that's it. That's what's happening at runtime, provided the values are not already known at compile time. Okay, you can see that. You can see this all. You can ask for the value. That's a runtime question, but you can also ask for the type and the unit. Decal type of C period is a unit, and numerator and denominator give you the ratio here. Let's divide it by 3.0, and let's use the count. That's 483.333 minutes, whatever the granularity and of double is here, or double values. And in C++20, you see here that the output is even simpler here. You can just write out the value instead of using count. And in addition, that output will add the unit. And it will use SI types, so standard types if possible. If not, it will do something else. We will see that in a moment. And of course, std format, the formatting library is supported. So we can see here, I want to use this in a way that this value, I should see how many hours, how many minutes, how many seconds these are. And yes, in 23, you can just use println here for that. That is where we got going to. Please note you cannot convert that to milliseconds because millisecond is an integral type, and we would have to trunk part of the value, so we would have to have a cast that narrows. But you can do something like rounding the values in different ways and then use a count and print out the value in both ways. So just to clarify how crazy this library is, let's do a similar example, 10 milliseconds, and that is a duration. And for some standard SI types, we have some standard fractions defined. std milli is just the ratio 1 to the thousandths. And then duration, we can have another duration, and that's 7.9. The value is 7.9, 2/3 of a second. And that's possible because every fraction, every ratio is possible as long as numerator and denominator are ints and inside int max. So again, we compute plus, but here the compiler has to do something more interesting. So what is the common unit of both? The compiler will find out at compile time. So the type of C uses 1/3000th of a second because that's because we have to add both, and that means the runtime computing that is generated is compute A times 3 and add then B times 2000 because that's the exact value. A, we divide the denominator, we multiply the denominator by 3, so we also have to do that with the numerator, and B, we divide we multiply the denominator with the denominator, that's the word, sorry. Denominator with 1000. So we also have to do that with the value, but we also in the past multiplied the numerator with 2, which we no longer do, so we have to multiply it with 2000. That's all happening during compile time. So the real generated code is what you see there. C equals A times 3, the value of A times 3 plus the value of B times 2000, which then at runtime is this if the values are only available at runtime. And you can pass that to any function that uses durations, like let's sleep my thread for that strange period of time, because here the standard library says I can deal with any duration. I will just knowing what the operating system needs, convert that to the right type. So we print out the value, and the same way we try to get converted to milliseconds. So if this thread timers need milliseconds, they would do the corresponding conversions. Again, you would not be able to convert into integral milliseconds, but you could convert, for example, into floating point milliseconds. That is not a standard type for that, but you can do that. Or you could round it again. So that's it. And then a third thing you should know is that we can use standard literals for that. So we have a couple of standard literals defined here. So you see at the beginning, where is my green? There, pointer. So you see here, there is milliseconds, 10 milliseconds, which is equivalent to declaring 10 milliseconds. Yeah, of course. Good. That's it. That's the basics. And with this basics, you can do a lot of things like initialize seconds, initialize hours. Let's subtract from each other. Well, if that narrows, it's a compile time error, but just computing the difference, that's fine. And as I said, conversions also, if they narrow, it will not compile. If they don't narrow, they will work. Yeah, I think we had that, yeah. Okay, and the underlying type is STD ratio, which is a compile time computing of ratios. So because ratios are used as types, so we do type computing, like let's divide the type 5/3 by the ratio, or by the type 25th, 15th, and give me the resulting type, as you see in the middle of this, and you will find out that that type, or that ratio, computed at compile time with template magic, is 1 divided by 1, because we even reduce to the lowest terms. That's used here. Good. First time explained. Next part of it, we also have time points. Time points are distances, so durations from a 0 point, from an epoch, as we say, and the durations are the durations we just saw, so they might have different granularity. The important point is that to combine two time points, to compare them, to subtract them, they have to refer to the same epoch, and an epoch is defined by the clock. And there are multiple clocks defined. Here you see one on the top right. It's a time point using the system clock, and we can use system clock now to get the current time point. The top line creates a default constructed time point, which is usually on POSIX system, the year of birth of POSIX, so January 1st in 1970. So we can compute that now with computing distances, defining different types, etc. And we can also convert this to a C-type STD time t, and then using C-time to make this readable as a calendar time. And that is happening here. But that was C++11, where we didn't have support for weekdays, month, etc. So you had to use the C library. That's gone with C++20. We come to that in a moment. Please note one thing: if you use a C library for formatting, you might use strftime. That's formatted. That's formatting into a string with a C function, and you see some specifiers here. These specifiers define the format you want to have here. Like here, we want to first have the month, and then the day with 2 digits, and then the year with 4 digits, and then %H is the hour, and %M, capital M, the minutes, both in 2 digits. We come to that later because what was then standardized in C++20 is a formatting library that adopts these specifiers so that you don't have to learn new specifiers for durations and time points. Finally, we have different clocks. So the most important 2 clocks from C++11 are the system clock and the static clock. With the system clock, you can just find out what is time, where's the birthday, so we communicate with the outside world about time points. And the static clock is just for measurements. And the idea is that it doesn't even get adjusted when in the operating system we change the system time. That is not technically always possible. So it always depends on the hardware, whether and how good that support is. But if there is support, you might, for example, say the static clock is not influenced by raising the clock of a CPU. So if you have this Pac-Man game, and after some time, and CPUs got faster and faster, then the game was over after 10 milliseconds because it was bound to the system clock. And the static clock should not be infected by changes of this clock, for example. So that's perfectly to measure. Measuring is very easy. Use a static clock now, time point. Do something, use another static clock now, time point. Compute the difference. The difference is the duration. You can round that duration against milliseconds, compute the difference, and you can, since C++20, directly write out the difference. And you see here that the difference here, when you subtract T0 from T1 directly, you see that obviously this static clock internally uses nanoseconds. And it's a smell that there are 2 zeros at the end of the value. So probably the granularity is 100 nanoseconds of this clock that's being used. Otherwise, I should play lottery or something else and I would win something. Yeah, that's it. And again, STD format can be used. That's it, I can skip that. We had that. Let me skip a few slides here. So that's it. That's the basics. Oh no, one basic I should say, I should show you. Please note, durations, when you initialize them, internally use the underlying type. So if the type is an integral type, a standard integral type, that might mean that objects of this class don't initialize the value. So if you declare something like a duration internally using int, that without initial value and without curly braces, you have an undefined value. Please beware. And that also applies if you declare a shortcut for that, like chrono minutes. M1 has an undefined value. It's not 0. And use, please, curly braces to make sure the value is initialized with 0 initialization. And the other thing is that duration values computations also follow the underlying type. And with the underlying type, you might have the effect that they overflow. So if you have here a time point of the default constructed time point, the default constructor of time point initializes with Unix birth or POSIX birth. Here's a function that does formatting and saying, let's see the year and the month and the day. And then let's add 50 years. So let's declare an object that is 50 years. So that's the ratio of 3,600 seconds times 24 days times 365 days. Oh yeah, we have years with different number of days, so that might not be exact. And you see now when we iterate over this, you see first of all that the month and the and the day are not stable because we skip leap days. But even worse, in 2219, we had an overflow in the year, and that was an issue here. And it's because the underlying type of this obviously was not big enough to hold that value. The funny part is, if you run that, and I did that today again with Godbolt, you can see that this is the output of GCC, and on Clang and Microsoft Visual C++, this works fine because they have a different type used under the hood. Maybe long instead of long or something like that. Yeah, that's it. Now let's go to what came in C++20. In C++20, we had direct formatted output. You have seen already a little bit of that. We have calendar functionality, so you no longer need strf F format, and then new alias name that helped there, time zone support, new clocks, and a few things more. Let's see how this works. So first of all, a couple of examples to understand how the library in general works. Let's have a party. We have a new suffix, that's single Y. So 2021 Y is a chrono year. You need std namespace, std_little's namespace for that. Std chrono year, that's a type of this thing. For that type, we have a slash operator defined. When there comes an int, we get a year combined with a month. So we interpret the int as a month. And then when we have another slash operator on that, then we get a year, month, day. So that's now something different. It's not a time point that has just a value that has a distance from Unix birth. It's a data structure with year, month, and day. And that can be used to initialize an object. You can change the order of initialization. You can start with a day or with a month. So we support all useful formats, the European one, the US one, and the technical one. And so let's iterate month by month over these days. So from first day, as long as we are less than last day, and let's have a party, and that's the output. That's it. Good. And here you see the third way. You can start with a month. We have predefined month values like std chrono January, and that can be used to start to initialize the first day slightly different. You can use std format to have a better output. Like here, let's print also the weekday and a different format, fine. Good. Let me start with the last day of January and iterate one by one, month by month. So this is the output. Yes, that's the output. That's the standardized output of that. It is the output of the second output. We hold the value that we add 1 month to a data structure holding a year, a month, and a day. So we only increment the month. So we have now 31st of February, and 31st of February is obviously not a valid date. So the default output format of that, and that standardizes, we print out the value with the extension is not a valid date. No, that's not localized. That's just for debugging. SD format is the right way to say what you really want. But you can see directly from debugging that this is not a valid day. I should say something. I was in a bank working one day, and because they had mainframes, they used dates like 31st of June. You can even see it on the bank report, on the monthly bank report that day to get additional taxes or so. And yeah, for that software, you would have to do some tricks here. So that also means it's not obviously a wrong date. It's just a date we don't know how to deal with that. And so how can we deal with that? That's easy. You can ask, it says, are you okay? And if not, Well, if yes, we print out the date. And if not, we have to decide what to do. And that might be take a different day. For example, the year and month first. So the first of the month plus 1 month. So it's the first of the next day. That is what we program here. But as an alternative, we have a type called, we can say, let's start not with the 31st of January, let's start with the last day. And that's funny because that last day is, by the way, not a value. It's part of the type because this object only stores a year and a month, and that then represents the last day of that month and that year. So we have a special type for that, year, month, day, last. And that, if you increment that, you see, yeah, the output is a little bit funny. You see the default output is last, but remember again, default output with the output operator is just for debugging purposes. The real way to deal with that library is to use std format, and with std format you can select the specifiers you want, and surprisingly these specifiers match with stdf format, so the C function we have plus some extensions. Oh, we don't want to have a party at Sunday. I have no idea why, but okay, that will look like that. Let's just check whether that day is whether the weekday of that is a Sunday. Let's look into this in a little bit more detail. First of all, we have a couple of data types, and we have a couple of suffixes and duration types. These are two different things. On the left-hand side, you see data types that are data structured that can logically hold one or more informations about a date. So like year, month, day last, and so on. That's a month, weekday, initializable with, I want to have the second Monday in February. You can see here, month, weekday, last, initialized with, I want to have the last day, the last Monday in this month. So things like that can be specified. And again, then you can combine that with a year, and you get a year, month, weekday, last, or something like that. This library is very type safe, so that it really finds out when you do stupid things. So adding another weekday to something that has already a weekday or specified last day, and you add a day to that, that will not work. That will not compile. That's the point. Good. And the other thing on the right, that's also a little bit funny. So we had the traditional duration types. You see them more at the bottom here. On the top, you see new duration types like days. And then you see something like years. So what is years? Well, that's the average duration of a year, which is, as far as you know, we have leap years. So we can compute that on average, a year has 365.2425 days. That's the values, because every 4 years we have a leap day, except every 100 days, except every 400 days we have it again. So that's the rule, and that's built into this. That means if you have a date, a canonical date, so a time point, not a data structure, a time point, and you add 10,000 years, you're pretty exact with the resulting date. It will be pretty fine. We also looked that we don't waste too much memory. So you can see a day needs 1 byte, a month needs 1 byte, a year needs 2 bytes, and the corresponding ranges. And the weekday, for example, is 1 byte. And you can see a year, month, day is 2 plus 1 plus 1, so 4 bytes. Perfect in our world. So that's the fastest thing we could have, and that's specified here. Okay. Let's go look at formatting. So these are all formatting specifiers for the std Chrono library we have. Several of them come from strf time. We adopted them, but there were also new things added like time zoned, etc. So a couple of funny things can be seen here, and most of it is worth explanation. There's a question in the audience. Yeah? Well, I can repeat the question if I understand it.
I know it's not for like another, like for day, month, weekday, evaluations are like all monthly or year, why do you value?
Which value do you have for a negative month? So you ask why is month and weekday and day always positive? I'm not aware of any month or any day that is negative in a month.
So like I guess before like 0 maybe it's like every year, so they're thinking about.
Say it again.
Or like the okay values for day, month, and weekday, like they're all positive.
Oh, okay value is all positive, but beyond what we have here. So the valid days are 1 to 31. So if you initialize day with 0 and you print that out, then the output will be I'm not a valid day. And it's a little bit funny. So for example, if you initialize day with 31, it might depend. So day 31 is perfectly fine, but if you have a year, month, day, whether that's a fine date will we find out when you print it, and we will see whether it's a leap year or not. Well, February is never okay, but in February, we even check whether when we use a day in a year, month, day, whether this is a leap year or not, so whether the 29th of February is a valid date. So we use that information to check off okay as good as we can. So without a context, we say everything that's possible and useful is okay, everything else not. And then when we have more context, like the days used in a year and a month, that might shrink to some situations that are not there. So 31st of February is always not a valid day, it's not okay. Does that answer the question? Yeah.
Question you talk about negative years, because you've got an okay.
Well, if you initialize that with a negative value, it will be converted to the corresponding positive value and you have an issue. It might work, it might not work. So that's the consequence of this. That's why I write it here, yeah. So don't use a negative day. That's all. Good. Other question? Yeah.
I'm still not 100% clear on this negative yet. What year is year 0? Is it what's the baseline for years?
Well, the year 0 is Jesus Christ's birth.
Okay, so it's like the Western 0.
Yeah.
Okay.
If you that depends on how it's interpreted, but yes, we apply on the Western world usually when we interpret that. Yes. Okay. So let's go to the formatting again. Just one information. Sometimes I'm asked, how about weekdays? So, no, excuse me, how about week numbers? So which number does a week have in a year? As you know, the weeks are counted. And this library knows that we have different standards for that. So we have 3 ways to count weekdays. So one way is the weekday number starts with Sunday, the other starts with Monday, and then the week of the year we have 3 different formats, but we only use that in formatting, where the one format is for week 1 has the first Monday. Then we have another format where week 1 has the first Sunday, and then we have the ISO week of the year, which is week 1 has January 4th. So yes, I had it once in my life that we had an appointment in a week number and we used different week countings, week number countings. So a lot of things from this talk will come from reality. It's not the fault of C++, it's just that's the way it is. And you see here that even things like that are supported. Good. So there's another interesting thing with this library. So we have now 2 different ways to deal with days. I could say I use a time point, the time point type, which counts from Unix birth. And the other type is the data structure, year, month, day. So both is possible, but now beware. Let me use year, month, day as a type of day. Let's initialize it with the first day and the last day, or compare against the last day, and iterate one month by month. So that works fine, as expected. Now, the obvious next trial, I always try everything, every stupid thing. Well, of course, it also works if we add day by day. Why not? Well, and you are surprised. No, that does not compile. So we cannot add one day to this data structure. What? Why? Well, of course we can. But the designer of the library said, oh, that has too bad performance. Because we can do better. Because when we have a day like 29th of February, what is the next day? Is it first? Well, not 28th is the interesting. So 28th of February, well, is it the next one 29 or not? That depends on a leap year. So to compute with single days, the data structure year, month, day is not appropriate. So we can do that, but numeric processing becomes slower. So that's intentionally not supported. Instead, switch to the canonical type, which is a time point type using the system clock and with the granularity of days. There you can add days, but there you cannot add months. Because, again, the duration of a month can be different. And so you see that when using this library, whether you use the canonical representation of a day or a calendrical, so data structure type, depends on what you want to do, what you want to compute. I find this pretty confusing. I'm not sure I like that, but that's the way it was designed. And it was designed that way for a good reason. We want to give you a chance to have the optimum performance. You can convert one way to the other, one format to the other. And that way it works again. So having said that, we can come back to our initial example that had the problems that we added a couple of times 50 years. So we had here the time point. The initial time point was the epoch. And then we added 50 years, which was an object that used the duration type. That means we use a canonical clock and canonical days from Unix birth, which is a pretty big number, by the way, beside everything else. And then we add in a loop 50 years all the time. Okay, you saw the output might or might not work. There might be an overflow depending on the granularity that's supported here in the platform. And there's a different way you can do that. First of all, look at the asString function we had in C++11 with using strf time. That is now very easy simplified. Let's just use a formatter and switch to the format we want to have. %f is the format we want to have. So which we also used here in strf time. So this is only one liner, probably not worth calling another function there for that. And the other thing is, now let's fix the bug. Now the bug is, let's switch to year, month, day, to data structures. And because 50 years is not a good way to add and it's fine to add to a data structure, and that works perfectly fine. So let's use the sysdays, the time point. We can convert it to a year, month, day object and print it out the same way as before with our generic formatting function, which takes both year, month, day and system days, which are time points with system clocks. And then here, now we define 50 years as being, 50 years. And then let's add that, and you see it works. It works for both month and year, and it works for the years and on all different platforms, because as you knew, we have 2 bytes for the year, so we can do this up to 32,000, to the year 32,000. You saw that before. Similar way, like breaking down year, month, and day, we have a data type to break down hour, minute, and second into one data type consisting hour, minute, and second. So again, you might have days 1, and you might print out, if I have half a day here, half 0.5 times 1 day, how many hours, minutes, and seconds are that? Just convert it to that, and you see by default with the corresponding output, this information, and with the member functions, you can access parts of this directly. Another way is to use SV format with %t for that, because that's a format, the standard format for year, month, day. Here's another example. Let's have 1,000 seconds converted to hours, minutes, and seconds. And you see 1,000 seconds are 2 hours, 46 minutes, and 40 seconds. And here's something even more interesting. That's one third of a second. And you see, by the way, the output format for that, if it's not an SI type, is 1. And then the fraction, the ratio, the unit is printed in square brackets. And then you can see, let's convert that to hours, minutes, and seconds. And you see that this data type even understands sub-seconds and prints them out if they are there. You can also access directly the sub-seconds, and that's fine to do. Let me run this program. Oh, am I online? No, I didn't prepare properly. But do we have enough time? Yeah, we are perfectly fine. So let me go online and then start this program in Godbolt with different compilers. And so let's go here. Thought I can click it. Can I not? I will never understand when PowerPoint allows me to jump to something and when not. So that's slide 42. So let me go to the slide here locally on my laptop. 42, of course 42. So that's it. That's the Godbolt thing. And you see here the program we just saw. And now let's see different compilers. That's GCC trunk, Clang trunk, and MSVC trunk. And what I wanted to show you is here that the default output format for microseconds is not specified exactly. So if the micro symbol is supported as a character, it will be used. Otherwise, it will be US. And that is here something notable maybe. And we standardize it that way. That's okay. Okay, how do I come back to my slides? Here, okay, good. So yeah, and format is also working. You can also pass dates. You can not only write dates on format, so you don't have the output way. You also have an input way for formatted input for timers and for time points and duration types. I'm not very happy. I tried it out a couple of times. Sometimes it worked, sometimes not the way I wanted. But anyway, here are examples that work. So you can see here, let's initialize an input string stream so that we read inside the program from that stream. We read with from stream with the corresponding format into a time point and print it out. And you see it there. And here is another example. Let's have here a year, month, day. And let's read into that. So the upper part is we read into a canonical value. And here the lower part, we read into a calendrical value or data type. And yeah, both works. In this case, works fine. But as I said, beware, not everything works fine yet, at least not the way I wanted to have it. So, this world has different time zones, and nobody can have a party with only in one time zone. That's ridiculous these days. So we have to have our party in different time zones. So let's do that. And let's see how we proceed here. That's surprisingly easy and surprisingly tricky, both. And so the first thing we do, we initialize a local day or local days data type. That's a canonical type, granularity days, using local time. So that's a pseudo time zone. That's a pseudo clock. It's not the clock of the system clock. We don't have specified the epoch in some particular way. We just have said that's local time. That's wherever I am. And we take this year, month, day and convert it to local days. And then we add 18 hours and 30 minutes. So that's 6:30 p.m. local time. So now let's combine this local time with a time zone. And that's pretty easy. So that way we convert it into a zone time and using, for example, the current time zone. Now I have a data type that holds a time point that consists both hours, minutes, date, hours, and minutes, and it's associated with a time zone. So let me print that out. And you see here in a loop, we do that month by month. We do it for the last day of every month in the year 2021. And that you see here the output. You see here that we use the formatter %Z to have the zone, the time zone that is used. And now let's invite colleagues in LA. And that's here. That's pretty simple. Take just a time point associated with the time zone and just initialize another zone time with a different time zone representing value or string. So you see this is America, LA, and with doing that, and then using formatting, a little bit tricky that we have 30 spaces here, and then we see that this is LA, and you see that the hours are corresponding changed, the time zones have changed, and you see also that usually when we have the meeting or the party in Central European time, though that's in Berlin, not here, and we have then the party at the same time in LA, there's a 9-hour difference, except in October, because in October, Middle Europe switched back to winter time, while in the US they still have summertime. And you also see things like we in Europe say S represents summer. In US they say S represents winter because it's standard time and not summertime, and we use summertime for that. So where do we get all these informations from? Because that means we have to know all the time zones in the world, and they are maintained. They are constantly changing. Some dictator in some country says, "Oh, I want to protect my people from having Ramadan too late. So let's change my time zone in my country." That can happen from one day to the other. So things like that happen. And we standardize in the C++ standard that we use the IANA time zone database. And that is what we recommend. So let's go to that. Let's look at this time zone database. Let me search for it. That's here. IANA time zone database. So it's probably, yeah, that's good. So you see we have a couple of information. So let me see, this is still, yeah. So the first two results are both interesting. Let's look at both. So this is a Wikipedia entry, and there is the IANA organization, which will tell you about this time zone database. And here you see how big it is. The complete distribution is 500 kilobytes compressed data. So that's a lot. And yeah, and by the way, there's also the whole history of all time zones. So when things change, in older days, we had a different time zones in different places. So this is all there. And the entries are versioned, etc., of this time zone database, and we can deal with that. So the other thing I want to point out is when we look to the Wikipedia page, which is pretty good about the IANA time zone database. So let's look. What is the thing on the right? I have no idea. Okay, so let's see. So you see every time zone has an identifier. Then we have an UTC offset. You see sometimes we have summertime, sometimes not. So you see that in Africa, Abidjan, they don't have summer and winter time. They just have GMT as a time zone. And yeah, you can see here all the places where GMT is used. It's also used in other places. So every time zone has a representative city, which is if a country only has one time zone, the capital, and otherwise there are different cities like Chicago for what is it? Eastern, no, Central Time. Yeah, thank you. Good. A few other things here. Let me just point it out. That has nothing to do with C++. This is more requirements for C++. So let's find out. Let me search for 44. And you see here that some time zones have an offset of 15 minutes or up or down beyond compared to UTC. So time zone difference is not always 1 hour. Everybody from India knows that because in India we have a half an hour offset. And then I also want to know something that is, let me search for CST. So now it's interesting. If you hear this talk in the US, you will say, oh, that's clear. That's Central Standard Time. But be careful. Time zone abbreviations are not unique. So let's see where CST is used. Oh, here, that's in Asia. The offset is 8 hours, plus 8 hours. So let's see somewhere else. Oh, there, Canada Central. Oh, the offset is -6 or -5 hours. And and there are other places that have it. I know one more, which is Havana. So where can I find it? There, Havana, which is -5 and -4. So CST can mean Central Standard Time for the US, Cuba Standard Time, and China Standard Time, which is on the opposite of the world. So the question is, if somebody tells you, let's have a phone call at 10 CST, and that's a phone call between US and China and Cuba guy, there's a good chance that we will never meet. And that can happen, but we have to deal with that in C++. And yes, we do that in this library. So you can see it here. That's, for example, a piece of code that can be used to find out in the standard, in the IANA time zone database, where are all the cities that have CST time zone abbreviation. So you see I have here an abref, which might come from the command line. If not, I use CST. And let's have here January 1st, 2020. And now here it's a call. That's a full time zone database. And with that time zone database, I can iterate over all the zones we have there, all the entries, get as the info, that's all the informations about these time zones. And there one member is the abbreviation. And now we can compare with that abbreviation and print out the data. And let me do that. Again, it's worth to see what happens on the different systems. Slide 47. I cannot talk and move my mouse at the same time. No, that's what's wrong. Okay, here's the code. Yes, I know, it's only for internal use. That's internal what we do here, huh? Good. So that's GCC, that's MSVC. It's a lot of data, it takes some time. and it took too long. Okay, let me turn off optimization, that compiles faster. That's a good way to make Compiler Explorer work if it goes out of time. Yes, we have time here to recover. Let's hope we see something. Okay, let's for the moment look here. So that's the output from MSVC. You see all the time points, the representative cities, yeah, all FCST, and you see beside of that, we have nothing else here. Oh, okay. So what does that mean? Am I wrong? No, now I have a result here. So let me look up the result here. And let's see. So here we have in Asia, Shanghai. So in Asia, Shanghai, it's 8. In America, Central Standard Time, it's 6. And where's Havana? There's Havana. Oh, it's 1 and therefore it didn't work. Yeah, that's 1 hour difference to that. So we have that. So let's go back to Visual C++. What do they do here? So where do they have Havana? Well, nowhere. Where do they have China? Nowhere. What's going on? It says Trump already? Just some tariff war? But okay, here's the information. Remember the slide which I had said something here. And that is Visual C++ has limitations. The point is, we require full support of all this data by the IANA time zone database. And that is a question of the operating system. We don't require it for a C++ compiler. So we say, operating system, please make sure that this is available. Now you can argue, you might have a nice idea what happens if these small Visual C++ guys goes to the strong Windows guys and say, we want to have in every Windows system in the world a new thing. That's the IANA time zone data with 500K of data. Are you kidding? I mean, it's not, I'm just, well, I don't quote anybody from Windows, so from Microsoft. So, but something like that has to happen. Yeah, they couldn't convince the C++ developers couldn't convince that Windows has it all, but that's a general rule. I mean, if you use C++ in an embedded system, a fire alarm or so, do you want to have a requirement that 500K of data is in this embedded system available? No, obviously not. So it's optional to what is available, and that was even funny. So here, this output works fine. But sometimes it prints just the German names on my system when I'm in Germany. And then I sent a bug report that was funny because Visual C++ takes the information from somewhere else, from the ACCU time zone support. And that is only limited information there. For example, they might not have the official American names for the time zones. They might only have the German names or so when I use that in Germany. So I sent a bug report to them saying, on my system, the time zone abbreviations are wrong. And then I got back, yeah, that's fixed. I just tried it out on my system. The person was sitting in America and said, yeah, it's fixed in the next version. And I said, are you sure? And yeah, so that can happen. All that means is, whenever you start with time zone information at the latest, please use try-catch, because try-catch will then, when you access informations like that and they are not available, you will get report from your operating system, from your runtime system about that. So what else do we have? Oh, and then we have clocks. Well, I told you already we have the system clock and the static clock. There's a third clock, which is a high resolution clock, which was a great idea to say that's a clock with the best resolution, and it should be separately implemented from these two clocks, but nobody did that. So in practice, it means it's either linked to static clock or to the system clock. So there's no really value in using the high resolution clock, although it is still there. But in C++20, we added new clocks: UTC clock, GPS clock, Thai clock, Phi clock, and local T. Local T is a pseudo clock so that we can deal with the local time zone. So that's a clock used there. Phi clock is a clock for entries of the file system, which might be different from the other clocks. So where's the 0 point, the epoch of the file system entries, and that might be a different clock. So ideally, if you take a file system entry, so when was it last stored, when do you have to read it, please clock cast it to a system clock to really print out the value. Otherwise, it might be wrong what you print out. And then we have UTC clock, GPS clock, Thai clock, that's International Atomic Time. So, and yeah, and what's that compared to the others? Well, the most important thing where we have differences is how to deal with leap seconds. So the system clock defines every minute has 60 seconds, end of discussion. The UTC clock says, no, there are minutes that have 61 seconds. GPS and atomic time also know that there are 61 seconds, but they don't care. They just continue. And when there is a leap second. So that has funny effects. So here you see the result. And you also learn something about this library. So see on the top, we have here the year 2017, January 1st. And then I subtract 1 second, so 1,000 milliseconds, to have the granularity of milliseconds. So that is the moment where we had the last leap second. That was the last second in the year 2016. So then let me convert to a UTC clock, because the UTC clock knows that there are leap seconds. If I compute with the system clock, then I will not see leap seconds. And so let's use this UTC clock. And the UTC clock time points now iterate in steps of 200 milliseconds. So, and then we take the current time point, we iterate over, and convert that to different clocks, to the system clock, to a UTC clock. It is already, therefore this is just gray. And convert it to GPS clock, convert it to a Thai clock or atomic time clock. And here you see the output, and that explains how the world is going on. So on the left-hand side, you see that the system clock has no idea about a 61st second when it exists. So what does the system clock do? It will, when we have the last second, that's here, it will then stay with the smallest value right before the first second of the next year or of the next day, and have that constantly there. So there are other ways in operating systems how things can be handled, like we clock down the system time for that period. So every second takes a little bit longer, but that's a very common approach. And that means for a second, all time points have the same value. Now, if you compute the distance between 2 time points and then use that as a divisor in some operation, then you divide by 0. And now you know why at a leap second, there's some risk that your system crashes, because if you're not prepared for that. And please also note, when we are here at the top line in the system clock, and I add 1 second, I'm not at the red line here, I go to the first second the next year. So I will jump over the leap second. So that means if you measure with a system clock, you will not include in your measurements leap seconds. If they happen while you measure, your result might be wrong. So the other 3 clocks know how to deal with that. So UTC knows that and says, yeah, okay, the last second in the year 2016 is, yeah, the second that has a value 60. So that's a 61st second in that minute. And then we switch to the next year. GPS and atomic time, they just count and count and count and count. They say there are no sleep seconds. Bullshit. We continue to run because otherwise we don't have unique time points, timestamps for each and every second. So you see, since GPS started, we had 18 leap seconds already because entries in GPS are now 18 entries ahead, 18 seconds ahead. And atomic time was standardized way earlier. So you can see here, epoch of GPS clock is January 6, 1970, and atomic time started in January 1st, 1958. So we have here now, we are ahead 37 seconds. The difference between GPS and TIE is always 29 seconds. No, 19 seconds, of course. Okay, that will be fixed. Please note, we cannot compute when the next leap seconds come. That's not possible. It's the astronomic experts say, oh, the moon is not at the right spot. We have to adjust the time. And when that happens, that will happen. And so what that means is we need patches in the operating systems for new informations, similar to time zone updates. And so you cannot compute ahead when we have it. There are currently discussions about that we wait 1,000 years until we deal with leap seconds again. And that's good. I'm not alive there. That's other person's problem then in 1,000 years. But they might then have a serious problem. Let's see. Okay. Good. So having said that, let's look at another program. And that program is print out the number of seconds in a year. And so with and without leap seconds, you might see the difference there. So let's take the 1st of January of that year and the 1st of January of the next year, year plus 1. So let's convert it to some clock, that time point, and then compute the difference in seconds and print it out. Here you see that's a, yeah, I don't know why I use here diff count. I could switch just to diff and skip seconds and count here. Yeah, because clock cast, the conversion from one clock to the other, that was introduced in C++20. So let's use a couple of example years and iterate over that. So here you see the different years used with the system clock. So that is, you see here, that's significantly more because we have a leap day in that year. So February 29 is in that year. And so we have either without February 29 or with it. Then we have the UTC clock. And the UTC clock, you see that we sometimes have a difference of 2 seconds or 1 second. Yes, we had a year where we had 2 leap seconds in 1 year. That was in 1972, the last time the case. And the same result you get with the other 2 clocks, because the other 2 clocks can handle also leap seconds, just in a different way. Okay? Good. Now we come to the conclusion of this talk. The talk asks how old I am in seconds. I know you're all sitting here because you want to know my age, but I don't tell you. I will say I was born in beginning of Carnival season in 1917. 70. Don't laugh. Yes, I made myself older. Okay. Okay. 11. So it's November 11 at 11. We start in Cologne the Carnival season. That's a very important date. So that is obviously the date I had to use. So let's pass this as a birthday. So a month, year, date, data structure, and a birth time, a duration that uses these 2 things. So let's, on the other hand, find out what time do we have now, and then see, convert that into a granularity of seconds, and round it to seconds, sorry. So that's now in seconds. And now let's convert the birthday and the birth time into system seconds and use the system clock to compute how old I am if I was born there. And of course, it depends when I start the program. So that might be the output. And now let's use, instead of that, let's use a clock cast to convert that system clock entries into UTC clock entries, because they can deal with leap seconds. And you see, it's significant more. It's, what is it? I'm 22, 27. I'm 27 seconds older than I thought. Oh my goodness. Half a minute. That had happened so far. Okay, you don't like the output format? Too many values? Okay, here just a trick, nothing to do with the Chrono library, just STD format allows you here to use the difference, and we use a locale, and in that locale we patched that we want to have thousands of operators. That's patched locales. That's something from cplusplus 98. You can use it there, and you can see, yeah. So we now, so a person that was born in 1970 is now 1,300,000,000 seconds old. That's it. And at the end, let's see how old I am now in my life here, and see what we have with the current situation. So you can see when the slides were prepared for how many seconds ago. Where is, yeah, there it is. So now we are here. And you see that both come up with slightly different results because they started the program at a slightly different time. That's it. That's all I have to say about the Chrono library and about the crazy world of time zones and time zone abbreviations and leap seconds and leap years and so on. Do you have any questions? Thank you.
Okay, I have a crazy question. How does the time zone or the Chrono library handle like March 31st, 340 BC? Can it handle stuff like that?
I'm pretty sure, yeah. So let me take that and see how many seconds we have since then.
That's a good one.
And that should be, what was it?
Well, I mean,
300?
340 BC.
300 faucet. So that's a negative value. Well, maybe that's enough. Let's compile. Because here has 2 bytes. So we can go up to minus 32,000 years. So that's the number of seconds you have there. Oh, you want to have it in a different format? I don't.
No, I'm just wondering how, for instance, if you're looking at a history book with the calendar changes that have happened, you know, are you
Oh, calendar changes.
like the
Yeah.
Gregorian calendar,
Um,
Roman calendar, stuff like that?
well, first of all, I should say that each and every time point entry uses a clock, and that clock defines a couple of things. And you can, by the way, and I skipped that slide, but you can look at that. You can, by the way, pretty easily define your own clock. And as you can also use your own data type for the values. So let's see how this works. Here you can see it. That's a clock, for example, that uses as epoch the moment when we started the program. So you can see here, I have a data structure, programming clock, and then you have to use some standard information like what is the granularity of my clock? What is the time point? Is it steady? That means, is it affected by the system clock or not? And you see everything is static or type definitions except one thing, and that is the question, what is now? So for a time point, what is it now? And here we say, yeah, let's take just an inner clock, which I use here. And this time I use a steady clock and subtract the moment when I started the program. And that moment, that means my inner clock has a time point 0 as starting point. And the whole library is generically implemented. So you see everything else you saw, you can do that like before. You can compute with time points, compute with durations, and so on. Howard Hinand has some examples, for example, of other calendars. So not just the Gregorian calendar, but other calendars. They are implemented with this library already. It's just we didn't standardize them. And so it's pretty flexible. I'm not sure whether we correctly handle what you want, but the library itself has this ability in principle. Other questions? Here's a question, yeah? You're waiting for the mic, or you tell me though, and I might be able to repeat.
Database lookup.
The database lookup.
If it happens or is able to happen at a context per time, can that be compiled out?
Okay, the database lookup. So you have seen that we can look up the database. And in that database, you can run a C++ program 30 years with that API. The way this works, you have to read in the database information again and again. And then the IANA time zone database has version numbers. So every change has a new version, and you can see what was changed has changed. And when the version is different, you can, for example, have to compute all your values again if you hardcore not the time point as UTC time point, but in some other way. So that is possible to do. It's not necessarily supported. Whether it's supported or not highly depends on the implementation of your standard library on the operating system. So when we say the operating system just uses some things from the C++ uses some things from the operating system that's hard-coded. So the usual way to update the time zone database as a reboot of the system. So with a patch from the system also. But the library itself allows something different. But then you would have to have the data, the time zone database available, information available yourself and read it in. In the reference implementation of this library, they do that. So you could even run 30 years and deal with all the updates you have. It's of course strongly recommended that you, inside your program, do every computation with UTC, and just at the very end, come up with the real format of the output and take time zone and other information into account. Don't compute too early the real output, the real day, the real hour, because it might be wrong and it might change over time. Okay.
Thank you.
Any other question? Okay, that's it. And I have to say, I want to thank Howard Hinnan, who is the author of this whole library. So I'm only the job telling about that. And I think this is a pretty well-defined library, taking a lot of things into account. Although some decisions I would have made different, but that's a good piece of work, I think. And I just have the honor with his help, and thank you, Howard, to present this library and explain it. He supported me very good when I wrote in my books about that. So thank you very much, Howard. And then I wish you a lot of fun with leap seconds and leap years in your future life. Thank you very much.